getting ready to, we're actually going to switch gears a little bit here. I think it's interesting. We've heard a lot about how fantastic and useful TinyML solutions are. Our next speaker is going to talk about where they're not useful and why TinyML applications fail. So please welcome to the stage Chris KNOROWSKI, CTO at SensiML.
Hi, my name is Chris KNOROWSKI. I'm the CTO at SensiML. And at SensiML, we've been working in this space for a number of years now. We've seen this conference grow from the small first conference that it had to the vibrant ecosystem that we see today. And we put together this talk basically based on a panel talk between our CTO, Chris Rogers, and Chris Rowan on the same topic, but it had a lot of interest. And I've been talking to several people here at the conference about why they think TinyML applications fail, and just listening to many of the conversations with the community. And my goal here is really to synthesize that information and combine it with our own experiences that we've had at SensiML, and hopefully be able to convey to you the issues that we're facing and help you navigate or be prepared to face the same issues. And as I've heard a number of people say here, only collectively can we move this field forward. To start with, I kind of want to frame this conversation by describing how I talk about what we do at SensiML to people that aren't in this field or this community. And so I basically don't mention TinyML or machine learning at all. I prefer to say that we're in the business of enabling devices to understand their environmental context. So that context could be a gesture, it could be a sound or keyword, it could be some anomalous behavior on a motor, but it all comes down to adding some algorithm that takes environmental data, collect it from a sensor, and characterizing it as a specific type of event. And to me, that's really what the promise of IoT is as well. All of these sensors everywhere, understanding their context and reporting it back or acting on it to optimize a greater system. For simple sensors like temperature or humidity, there's really no need for a complex algorithm. And that's a lot of applications are that way, where they're simply interested in aggregating that sensor data. But for more complex sensors and more interesting use cases, you really do need to start using machine learning to characterize that sensor data. Not necessarily TinyML solution, but ML certainly. And as more of these sensors get added, if you continue to stream and collect data, the systems get bigger and more complex. It starts to make economical sense to move the processing closer to the sensor versus sending it out to the cloud. And I think for me, that was the initial vision for where TinyML can really come in and provide a lot of value to make these larger systems scalable. So in addition to that vision, there's many other areas where it just makes sense to do the processing closer to the edge because it makes for a better user experience and also makes applications that without it just wouldn't have been feasible at all. So how do we qualify if TinyML is the right tool for an application? So for every new customer or POC that we come across, I typically go through a checklist to validate if the problem warrants the additional logistical complexity that comes with deploying these on embedded applications. So if I can qualify that a customer doesn't indeed need TinyML, I know they're much more likely to complete the project versus switching to a more traditional approach or just leaving out that feature entirely. So first, I always want to make sure that the problem's tractable in general. Giving the full resources of the cloud, are you able to solve this problem? The other side of that is to make sure the problem's suitably complex enough that it needs machine learning. If it's a simple threshold detect for excessive vibration, there's really no need to set up the entire machine learning pipeline. So how do you know if a problem is suitably complex? That's typically when machine learning makes the problem scalable, meaning that the solution that would be a hand-coded heuristic to solve the problem might be too brittle or just not general enough. And keyword spotting has really been kind of the killer application, I think, for TinyML. That shows how machine learning's made it scalable. So a hand-coded solution might work great for a single speaker or a few words, but machine learning's allowed us to solve that problem for many speakers, words, different backgrounds, and all sorts of different noise. So once that criteria has been cleared, the next I look for something that makes TinyML the right solution versus streaming data back to the cloud. And so one of those is security and privacy. So if the data needs to remain on the device, and they need it to make a decision, then TinyML is typically the right choice. And we're seeing a lot of that in the community right now. The next is latency. So how quickly do you need the response to happen? If you're detecting a drill bit that's about to break due to some excessive stress or vibration, then you need to know that immediately on the device, and that added latency or round trip can make it too long. So that's another thing that really drives a TinyML solution. Connectivity is an obvious one. So if the sensor data or application is deployed in a remote location, or the sensor exceeds the bandwidth of the network that it's on, then it really makes sense to do all of that processing locally. And power goes along with connectivity. If you can extend the battery life by doing the processing locally, you can start to push these devices from months to years in the field. And finally, the economical benefits. For TinyML applications, often the cost of the hardware and the power budget are just as important for accuracy, at least for in some different of the market segments. And so one of the people I was speaking with yesterday phrased it, I think, very succinctly, where they said, if you're integrating a TinyML application, it must be more than incrementally better than what the company's doing now to justify the investment. Or it has to be something that's creating an entirely new market segment that just wasn't there before. Let's see. So with that criteria in mind, what are the steps to build a TinyML model? And basically, we all know this kind of standard flow. You start with raw signal capture, you do data labeling, algorithm generation, firmware generation, then we test and validate. Then we find we did something wrong, our model's overfitting, we have to go back to these previous steps to improve the model. And I would argue that as a community, we're very, very good at building TinyML models and this entire process right here. And if I just look around at all the sponsors that we have today, there's tools that are built, that we've built for these TinyML models. So we have microcontrollers, low-powered sensors with high accuracy, hardware accelerators, platforms for AutoML, labeling tools, connectivity solutions, great compiler options. There's security for the deployed IP on the device. There's not so much around modeling things in the field or full end-to-end solutions that we have to showcase together, but we've built all of these tools for TinyML models. So the question is, why are we still seeing TinyML applications failing, or why are we having trouble seeing the adoption of these tools that we're building? So, and I think a lot of it comes down to the fact that building a TinyML application looks a lot like building a software application in terms of the customer engagement, but in fact it's quite different. And I think one of the things there needs to be is just a lot more education around what it takes to build that robust TinyML application to help improve that sales cycle. There we go. Okay. So what does it take to build the TinyML application? We see a number of different types of engagement as a SaaS tools offering. Some of our customers come and they want to do everything. Some of them need some help data collecting. Some of them want us to help them do everything. And so we offer those different services, but I think in general, even if they're building the model themselves, they're going through these same steps. So first thing that happens is the customer comes and they say, I want feature X. And we as a company building these sort of tools need to be careful here, because we obviously want to evangelize our technology, but as we get more experience with what works and what doesn't, we're careful about saying if this is a good use case or not for the technologies that we're building. And so I always try and think back to those earlier rules, like, is the customer going to follow through with this feature? Does it really make sense for them? And the second step is usually we'll do an initial demo with our tooling on some POC that we have that's kind of related to what they have with a similar scope, or a small mock-up of what they want. And at that point, we're trying to convince ourselves that what they want is possible. We want to understand the problem scope a little bit more. And then we need to convince them that what they're asking for can be done. Then we typically come up with an SOW for their specific application. And that's going to outline the work that needs to be done, so the scope and the cost of the initial project for their application. And in this proposal, we're typically stating some sort of data collection plan. And this generally ends up being one of the more difficult parts of the engagement for us. There's all sorts of hurdles around data collection, depending on the type of project that they're working on. And these companies typically aren't that experienced with that data collection process. We have challenges getting the right test subjects, getting data off the device, calibrating the sensors. And I can go on and on for all of this. So, but typically we'll see that, oops, I'm one behind. Yeah, this is like a 1 month to 3 month process at this stage within the POC. Sometimes shorter, sometimes longer. And then finally, once we've got our data collection, we build the model. If it works well, and we'll test and validate it on their device, and we'll integrate it into the POC, and we have lots of tools for doing all of these things. And then you end up with the customer that's happy, and now they want the POC in their product. But if we think back to the data collection, building a TinyML model, this is actually really an iterative process. So from a software engineering feature perspective, they're usually expecting, okay, you've built the POC, now let's integrate this into the product. But we know from our experience is that the POC is typically like 80% of the way there. And there's a lot of work involved in making that a robust model that's production ready, and that can take many iterations. So that can make them very sad. So at this point, what can happen is you're going to start talking with other stakeholders in the company. So we've done this POC with one part of their team, and now we need to decide if it's going to be included in their product. Are we going to take it forward to production? And I think a lot of here, in this area here, a lot of the education needs to be done early on to make sure all the stakeholders involved know. So if you haven't discussed up front, you could run into issues around the business licensing, around royalties, purchasing outright. Internally, they may have been thinking of you as a consulting role and not expect to have to pay for the model development. Beyond that, if you aren't taking a holistic approach to the entire application, such as the sensors could be different in the final product, the placement could be different, they could have a different enclosure surrounding the microphone with different characteristics. You can run into many of these issues where you've proven out the POC, but now you have to go back and do a lot of the work when you want to bring the model to production. So the two kind of takeaways from this here is make sure you're defining the application and understanding the economics of making it viable. You almost need to treat the customer as an adversary at the beginning to make sure what they're asking for is what they really want. So are you sure a simple button wouldn't be better? We worked with one company that was developing a smart shoe that would automatically lace when the customer put their foot in it. And they wanted to use basically an accelerometer to do this. And we were just really worried about the false positives and all sorts of other issues that are going to come up with that, where either a different sensor would be better or a different approach entirely, not a machine learning approach in that case. And second, it's worth spending a lot of effort early to identify all the stakeholders within the company and educating them on what it takes to build that robust model, not just the POC. So make sure that the feature is something that it's really worth our time investing in trying to create. And I think collectively, the more we can grow our knowledge about what doesn't work, the more we can focus our efforts on what is going to work. And I just want to point out I don't really discuss in this talk deploying the models that much in production, but the TinyML group did put together a really nice white paper that goes into a lot of details on what you can expect when you put these into the production, so it's definitely worth checking out too. So I talked a bit about the process of building a TinyML application, but what are things to look for to see if the application is going to be successful or not? And I think there's really three pillars. Three pillars that you can rely on. And the first is you need to have someone that has machine learning, data science, or analytics expertise. Someone that can take a physical sensor data, construct a data set, and implement that within some AI framework. Next, you need to have someone that really understands the nuts and bolts of microcontrollers, the hardware, and the connectivity. And finally, you need someone with that domain expertise. And so when you're going to start the project, you need to make sure you can identify all those resources within your company and the company you're working for. And I think it's really our goal as a community to remove as many barriers as possible so that we can provide value, so the customer really just has to bring their domain knowledge and expertise. So with that said, I want to spend a little bit of time just discussing some of the more specific parts of the problems that we face in some more detail. So the first one is the data collection and annotation effort. And one of the first questions we always get is, how much data do I need? And we pretty much always answer, it depends on how much variance is in the data set for your problem. So for models that we've already collected a large amount of similar data, transfer learning can be used. For the audio and image realm, you can use augmentation. But for more custom use cases, it really can be, you can't really rely on other outside data sets. So we typically will we'll have them stage their data collection efforts on a smaller number. So if it's some sort of activity recognition, we'll start them with 10 subjects first, build the model so we can really quickly start that test and validation process to get going. So here's, and when you're doing that data collection, there's lots of tools out there. We've invested pretty heavily in building out a labeling tool for time series sensor data. Can you hit the, so you can use, I would definitely suggest just making sure you're familiar with how to quickly label data, how to segment data, how to use models to go through and label your data. So here's our data capture lab for audio data. And then we just have automated segmentation built in so users can really quickly go in and label their data and use tools like these to manage their projects to get a high quality sensor data at the end. So another thing to do is make sure you spend time defining the scope of the model. And the challenge here is often defining the scope so that it fits within the data collection resources you have. So the main one of the example I'll talk about here is we were working with a company building a wearable device that detects swimming strokes. And it became apparent that we needed to define, is that me? Okay. We needed to define the type population of swimmers that we wanted to build the model for, because we didn't have time to go out and collect data for every single type of swimmer out there. So it made sense to focus first on the expert swimmers, because their techniques were much more uniform than the general population of swimmers. And the general population would swim in a very different way. So here's an example up here where we have the swimmer, and she's a really great swimmer. She swims her laps in a nice uniform fashion. All of the strokes are very consistent. But in the other case, we have this guy, and he's resting a lot, but then he's also just swimming with his head above the water. And so there was really no way for us to, within the context of this project, to go and collect all of that sensor data for all of these different types of use cases that come up. But this is one case where personalization would work really well. So if you have some sort of on-device learning, you could have the user put the goggles on, swim the 4 different strokes, and then just calibrate and tailor towards them. So some of the techniques that are being developed now would really make that a lot easier problem to solve. Okay. So the next is slow test and validation iterations. So this can happen a lot when you're working in remote teams. So you can have for us, it happened where we had the hardware team that had the device was in a completely different location. We didn't really have access to it. And it took them a long time to even get the data collection off the device. And then once they had that, it was really difficult for them to get the model onto the device just because of the way their firmware worked. And they couldn't give us access to the device or the firmware. So it was really important for us to come up with good ways to test and validate that really quickly. And one of the things we've come up with is just inside our data collection tooling. Now we can stream the sensor data and run the model at the same time. So this is one of our users put this video up, where as the data is streaming in, it's running and it's labeling the data, so you can get a very clear picture of what does your sensor data look like and what does the classification look like, and you can record that along with the video and go back and analyze it later. And it just makes life so much easier when you're working with these embedded applications. If you don't even have to go flash the device, you can just start testing right away. How much time do I have? 1 minute, okay. Yeah, so I'm just going to skip these and kind of go to the final thoughts. So basically, some final thoughts are just make sure you qualify the application holistically. Spend time educating the customer on what it takes to build that robust application so you don't get halfway through the process and get stuck. Spend some time identifying the resources that you know you need to be successful. And then as a community, let's just talk more about what hasn't worked so we can focus on what does. So, thank you.